Hello everyone. I'm Dr. Shonak Bansal. Presently, I'm working as a faculty in the Department of Electronics and Communication Engineering at Chandigarh University, Mohali, India. First of all, I would like to thanks to the journal Result in Optics for accepting my paper entitled with Long Wave Bilayer Graphene Mercury Cadmium Telluride Based GPP Type II Superlattice Unipolar Barrier Infrared Detector in 2023. Now, I would also like to thank the organizing committee of Science Father for selecting my paper in the best paper category and giving me the honor as a best researcher award. So photodetectors are basically known as photosensors, which sense the electromagnetic radiations, or we can say incident light. So they are the sensor of the electromagnetic radiations or incident light. Photodetector are the optical receiver unit in which a PN junction is reverse bias that converts the optical signal to electrical signal. Hence, they are referred to as the optoelectronic converter. Basically, photodiode is, we can say, it's a reverse bias PN junction diode with junction exposed to light. Photodetectors are made from some semiconductor materials such as silicon, germanium, third, fifth base group material, second, sixth base group material, and nowadays we are using the two-dimensional material like graphene and molybdenum disulfide. Photodetector found their potential application in the field of the fiber optic communication. They can be used as interconnects. They can be used to detect the terahertz range. They can be used in the military, imaging, remote sensing, surveillance, and spectroscopy, and etc. Basically, photodetector work in two mode of operations. One is the photovoltaic mode and second is the photoconductive mode. Photovoltaic mode is the mode in which diode is operated with no applied bias voltage. Whereas in the case of photoconductive mode, we apply the bias voltage to collect the charge carriers. So photodiode is we can say it's a current source with or without the bias voltage. Now we have the basic steps of photodetection. Whenever light is incident on the photodetector, the photosensitive material will absorb this light and will excite the photogenetic electron to the from the valence band to conduction band. It means there is a transportation of charge carrier across the depletion region, and these charge carriers are separated by the external electrode by applying the reverse bias voltage. It will give us the net photocurrent through the external circuit. IR detectors. Now, IR detectors have been successfully demonstrated with the wide variety of narrow bandgap semiconductors such as silicon, germanium, alloy, including third, fifth group base material and second, sixth group base material. These material will absorb the incident photon energy corresponding to their band gaps and result in the output photocurrent. So, infrared detection range is categorized into short wavelength, which is from 1 to 3 micrometer, mid wavelength, long wavelength, and very long wavelength regions. Mercury current and graphene are most widely used material for the development of the IR photodetector. The rapid advancements are being made in developing inexpensive narrow bandgap semiconductor detector with improved sensitivity and long wavelength. As a result, lower dimensional materials such as quantum well, quantum dot, quantum wire based IR detectors are also reported with improved performances but with expensive fabrication processes. So IR detector has their potential application in biomedical and thermal imaging, gas sensing, night vision, spectroscopy, and free space communication, etc. Now the property of the mercury cadmium telluride materials. Mercury cadmium telluride is most widely used material for the development of the infrared photodetector because of its excellent properties such as tunable band gap, low leakage current, better stability, low thermal generation rate, and relatively high absorption coefficient, which make this alloy as a suitable material for the high performance IR detectors. So far, numerous mercury cadmium telluride based IR detector with different configurations such as PN, PIN, and dual band IR detector have been reported at cryogenic temperatures. The band gap and band gap affinity and intrinsic concentration of mercury cadmium telluride depends on the temperature and X composition of the cadmium. So depending on the wavelength, or we can say cutoff wavelength and temperature, we can tune the band gap of the mercury cadmium telluride by changing X composition of the cadmium. And cutoff wavelength is the wavelength at which the response drop to 50% of its peak value. So these are the equations which are used to find the band gap, affinity, and intrinsic carrier concentration in the case of the mercury cadmium telluride. Graphene. Now, graphene is basically two-dimensional crystalline allotrope of the carbon atom which are arranged in the honeycomb or hexagonal lattice. We can see here they are in the shape of the hexagonal. Hence, 2D means layer material only a few thick atom thick, and there are two bands at which 6 points are there, and they are called direct point or charge neutrality point. The point with highest resistance is known as the direct point or charge neutrality point, at which density of state tends to 0. So because of the lack of the band gap, graphene is usually described as a zero band gap material, or we can say simply call this as a semi-metal. Graphene has unique electronic transport property, which make graphene as an excellent material for advanced application in future electronics. They have the high mobility, around 10 to the 5 centimeter square per volt per second. But in the case of silicon, it is 1000 centimeter square per volt per second. So we can say they have a high mobility, which is 100 times higher. They have large conductivity. They have broad spectrum range. They can have the ultraviolet to infrared region. High current density means graphene has the high electric field, and due to this property, it has been assumed that graphene can carry the large amount of current. So these we can say extraordinary property make it suitable candidate for new optoelectronic technology both within or beyond the CMOS technology. Also, graphene can absorb a single layer of graphene can absorb the 2.3% of the incident light from ultraviolet to infrared region for a single pass, and bilayer will absorb it twice as much, and so on. And in graphene, electron move much faster than the normal electron, means they have the high Fermi velocity, which is 1 by 300 times of the speed of light. Now, advantage of the graphene-based detectors. As I already taught, the excellent electrical and optical property of graphene enable utilization of graphene as a transparent electrode integrated with conventional detector for ultraviolet to infrared region. They have the long wavelength operating range. They have the high speed of operation due to their high carrier saturation velocity and short carrier lifetime. Graphene can be integrated with the system as well as device, so they can be transferred to any substrate, hence integration is made easy. Graphene composite consisting of graphene and other material combined with the high carrier mobility of the graphene and the excellent light absorption property of the other semiconductor. So we can say graphene composite photodetector are the one promising candidate for development of the next generation photodetectors. Graphene, we can tune the band gap of the graphene, or we can say we can tune the Fermi level either up or down by with the help of doping or with the help of applying the external gate voltage. Graphene has been successfully composited with different materials such as zinc oxide, silicon, cadmium sulfide for the ultraviolet application, gallium nitride for visible application, silicon, germanium, lead sulfide, gallium arsenide for the IR applications. The graphene semiconductors such as mercury cadmium telluride heterojunction based photodetector are expected to demonstrate low dark current, low power dissipation, small parasitic, high breakdown voltage, and high response speed than that of the conventional homostructures. Now, we have some challenges with the graphene based detectors. However, the conventional graphene detector normally depends on the photoconductive mode that typically have limitation of the high dark current at room temperature. Most of the IR detector based on the graphene and mercury telluride are not viable for room temperature operation because the thermal excitation at room temperature would generate large dark current that is comparable or even higher than the photocurrent. Additionally, zero band gap and small optical absorption of monolayer graphene, which is 2.3%, offers limited photocurrent responsivity, photosensitivity, which is the ratio of the light current density to the dark current density for the graphene-based photodetectors. So, accordingly, several efforts has been done to improve the performance of the graphene-based photodetectors, such as use of the fuel graphene, graphene quantum dots, including small gap in graphene by using intentional doping. Means we can shift the Fermi level either upward or in downward direction, which will create the suitable band gap opening in the graphene. Or extendable spectral response to long wavelength by making the heterostructure with other semiconductor materials such as mercury cadmium telluride. It has been demonstrated that already transferring few layers of graphene around on the mercury cadmium telluride substrate offers a high conductivity, which is 25 times than that of the conventional one, and optical transmittance of 80% in the mid wavelength spectral region at cryogenic temperature and the room temperature. Now, in my this research work, I have used the p-type graphene. So the doping of the graphene is achieved by chemical agents such as nitric acid, ferric chloride, gold thiochloride, trionyl chloride, niobium chloride, implementing by the chemical vapor deposition technique. To the best of my knowledge, a maximum band gap of 430 millielectrovolt is found to be in p-dope bilayer graphene. This will increase the carrier concentration and thus increase the conductivity of the graphene layers. So coming to the type 2 superlattice unipolar barrier IR detectors. So basically type 2 superlattice is a material, or we can say it's a structure that comprises of thin layer of different materials. The excellent band engineering capability of type 2 superlattice material system allow each part of the device to be carefully tuned to use detector action to realize low noise, high efficiency, and high detectivity. Sometimes mini bends arise in the material if the layer thickness is sufficiently thin in quantum mechanical sense. This results in a synthetic material whose property can be changed. In detector case, if we talk about in the case of detector, the band gap energy matches the required cutoff wavelength. So we can tune the band gap according to the wavelength. The flexibility of the material allows the integration of barrier IR detectors to filter out the generation recombination current and improve the detector performance. Among the various material, graphene, mercury telluride heterostructure are found to be favorable type 2 superlattice choice due to their tunable band gap and self-passivated surface, and can be used to develop IR barrier detectors where interface defects and lattice mismatch can be avoided. Among these several graphene and semiconductor heterostructure, graphene mercury heterostructure is chosen to demonstrate superior optoelectron capability in the IR spectral region. The electric field at the graphene and mercury heterostructure interface also efficiently isolate the photogenetic carrier, thus preventing recombination. Therefore, detector with unipolar barrier heterostructure interface architecture are an effective choice to suppress majority current, that is the dark current, density and noise level, thus enabling IR detector to operate at high temperature with a high signal to noise ratio in comparison to the conventional PN detector. The barrier layer must be carefully chosen with suitable lattice matching and band alignment in order to limit majority carrier current density while allowing the passage of the photocurrent density. At barrier active layer hetero interface, such detector introduce a increased band offset in conduction band and almost zero in the valence band to filter out the surface leakage current density, leading to the minority carrier dominated transport. The large valence band offset in barrier IR detectors results in the limiting photo response. Therefore, proper doping at the hetero interface between the contact barrier absorber should reduce banishment offset. So in this work, the heterostructure and band engineering capability of bilayer graphene are considered along with the type 2 superlattice match mercury based material layers to realize a novel structure of the self-power type 2 superlattice detector in long wavelength infrared spectral region. The detector structure consists of the bilayer graphene as a narrow bandgap contact, or we can say cap layer, a thin band, a thin large bandgap material as a murky connector as a barrier layer, and then a narrow bandgap p-type active or absorber layer, and is termed as a GBP LWIR detector. That is a long wavelength infrared detector. The active layer, the functional active layer will approximate the current density, whereas the contact layer will provide the biasing. And this study is the first to examine the optoelectronic property of the graphene barrier and active layer detector for the long wavelength infrared spectral region. The obtained dark current density of the proposed this device is analytically further validated by using diffusion and tunneling current methods. So these are the parameters which are taken for the simulation purpose, and the device has been simulated using the Silvaco TCAT software. So these are the parameters for the contact layer, barrier layer, and the active layer. Now moving to the electrical characterization, the proposed unipolar barrier detector is simulated by numerically solving the carrier current continuity equation and Poisson equation with suitable boundary conditions based on the Boltzmann transport model. In bilayer graphene, the semiconductor drift diffuser model is utilized to evaluate the carrier transport processes. To further demonstrate the barrier blocking phenomena of dark current density in a unipolar proposed detector, the spectral distribution of current density component is shown in this figure as here. So placing the barrier layer in the unipolar detector will filter out the surface leakage current density, majority carrier dark current density, and re-injected light current density while allowing the passage of the light current density and diffusion current density and auger limited current density. This is a schematic of the energy band diagram and the electric field profile for the proposed detector under IR illumination and self-power mode. At interface, junction barrier exists as a result of the distinct work function of the bilayer graphene and mercury telluride. Upon joining, the differently doped region under suitable equilibrium conditions carrier diffuse due to the carrier concentration gradient, which bends the energy bandwidth at the interface until the Fermi level is aligned properly. As it can be seen from the figure that the whole barrier is made to provide a large potential barrier in the conduction band and a small or negligible um, offset in the valence band by using both the p-type materials. The connection offset, we can say connection by offset is found to be 322.2 milli electron volt, and valence band connection offset is found to be 46.39 milli electron volt. The electric field will help to separate the photogenetic carrier at junction. This electric field dominates the heterojunction and is enhanced by the external biasing voltage. We can see here this is the profile of the electric field profile at the different junctions, and it will increase with the applied bias voltage. The electric field is mainly distributed in the barrier layer. We can see here it is distributed along the barrier layer due to the existence of the high barrier resistance. It could be seen that there exists a high electric field at the graphene barrier interface, which is essential to quickly separate the photo-induced carrier, limiting carrier recombination and exhibiting quick response time. The maximum electric field at self-power mode is found to be 52 at graphene barrier interface and 25 kilovolt per centimeter at the barrier active layer interface. Whereas at the biasing of the 0.5 volt reverse bias, the maximum electric field is found to be 236 kilovolt per centimeter at the graphene barrier interface and 41 kilovolt per centimeter at the barrier active layer interface. So under the illumination, the photo-induced holes in the active layer flow to the anode across the very small valence band offset, whereas photo-induced electrons are quickly separated by the cathode under the high reverse bias condition, thus causing the flow of net photocurrent density into the external circuits. The non-linear current density, dark current density voltage characteristic in the log scale is shown in the figure A. The dark current density will increase with the applied voltage, which is attributed to the dependence of the conduction band offset on the bias voltage. And it is also noted that the proposed unipolar detector show a smaller reverse dark current density than the forward current density, indicating that there is the existence of the junction barrier in the proposed detector. The proposed unipolar detector show the dark current density of the 1.7 into 10 to the minus 17 ampere per centimeter square, whereas light current density is found to be 3.2 into 10 to the minus 9 ampere per centimeter square. And the ratio of the dark current density, sorry, photocurrent density to the light current density is found to be 10 to the 8, which is much higher, or we can say light current density is the 10 to the 8 times the dark current density. So this will result in the high specific detectivity and high signal to noise ratio. The similarity value as shown in figure will closely match with the analytical expressions in the reverse bias mode. The dark current density value for the proposed detector is found to be superior than that of the other graphene and other two-dimensional materials. Such a low value of dark current density in the proposed detector is due to the presence of the lattice matched large bandgap barrier layer that provides a large band offset in the conduction band and a small or negligible band offset in the reverse band, in the valence band. This barrier layer will allow the photogenetic minority carrier to flow to the electrode while the majority carriers dark current density, surface current density, tunneling current density, and re-injected light current density are filtered. Moreover, the shorter carrier transport path with bilayer graphene as a contact layer in the proposed detector would considerably reduce the recombination probability of the photoexcited carrier in the superlattice structure. Bilayer graphene, in contrast, has broadband transparency of the around 95% in the IR region, which allows light to penetrate in the detector. Therefore, a much light current density is found as compared to the dark current density in the proposed detector. This figure B, that is the figure B, will compare the dark current density value of the proposed detector under the bias, that is the photoconductive mode, and non-bias, that is the photovoltaic mode, with the rule 7 and law 19. And the proposed type 2 superlattice detector exhibited reduction in the dark current density by two order of magnitude than the rule 7 and 19 under the photovoltaic mode. Now this figure shows the normalized photo response of the proposed unipolar detector as a function of the light intensity modulation frequency at a bias of the minus 0.5 volt. The photo response curve is normalized to start the response at the 0 decibel and the 3 dB cutoff frequency is found to be 0.39 terahertz, indicating that proposed detector can be used for terahertz frequency applications. And the response time is found to be 0.87 picosecond, which is less than the 1 picosecond. In order to find the noise current has been found, and this former part is known as the short noise current, and this part is known as the later part is known as the this part is known as the thermal or Johnson noise, and the second part is known as the short or quantum noise. So this figure will compare the Johnson noise and the short noise under the applied bias voltage. Generally, both the Johnson noise and short noise contribute to net dark density. The short noise significantly increase. You can see here, this will increase with the applied bias voltage because the darker density is large and become the main noise source. As shown in this figure, the noise contribution due to Johnson noise is small as compared to the short noise, suggesting that the undesirable thermal generation recombination current component is efficiently filtered out with the existence of the barrier layer. However, for the more accurate estimation, both the Johnson noise and the short noise are considered in this work. And the total noise current is found to be 1.1 into 10 to minus 17 ampere, and signal to noise ratio is found to be 132.50 decibel. To further illustrate the performance of the proposed detector, the optical characteristics parameter, including photogram responsivity, quantum efficiency, specific detectivity, and noise equivalent power are estimated. The variation of the response current, photogram responsivity, and quantum efficiency with the applied bias voltage is shown over here, whereas this figure will show the variation of the specific detectivity and NEP with the applied reverse bias voltage. It is clear that with the increase in reverse bias voltage, the responsivity, quantum efficiency, and detectivity will increase, and hence noise equivalent power will reduce. The increase in photon responsivity, quantum efficiency, and specific detectivity with the applied bias voltage primarily attributed to the higher drift velocity of the photogenetic carrier as well as the greater likelihood the excited separation and acceleration with the voltage, which finally generates the photocurrent. This specifies the photoelectric gain due to the flow of the minority carrier over the barrier layer. The increase in quantum efficiency is caused by the carrier rapidly passing through the thin depletion layer under the applied reverse bias voltage. And it has been found that the quantum efficiency of more than 100% is achieved. You can see over here, the quantum efficiency of more than 100% is achieved for the proposed detector in the long wavelength infrared region. The obtained quantum efficiency of the around 186.52 at bias of -1 volt is much higher than that of the previously reported mercury carrier telluride based detector. This more than 100% efficiency is due to the combined effect of the hot carry multiplication effect, external bias voltage, and a high electric field across the heterojunction and significant potential barrier in the conduction band. Under the hot carrier multiplication effect, numerous carrier from a single incident photon in the bilayer graphene are generated, or we can say a single incident photon will excite one valence band electron to the contact layer to the conduction band, which further stimulating the other valence band electron to move to the conduction band. Such an inverse non-radiative Auger recombination process, which is known as impact ionization process in the bilayer graphene, results into the hot carrier multiplication effect. The estimated photogram responsivity, quantum efficiency, detectivity, and noise equivalent power is found to be this value with the voltage of the from 0 to 1 volt in the long wavelength infrared region. This large photo response is attributed to a diffusion current of the photo-induced carrier in the active layer. This indicates that the valence band offset is small in the proposed detector. So these are the this table lists the comparative summary of the optoelectronic property at cutoff wavelength, which is 10.6 micrometer, and reverse bias voltage of the -0.5 volt for the proposed detector. And it has been found that this proposed detector will show the superior performance than that of the previously reported detectors in the IR region. At last, in the conclusion, in this work, a unipolar graphene barrier and active layer unipolar device has been designed to work in the cell power mode in addition to the bias mode operation and terahertz frequency application in the long wavelength IR spectral region. The optoelectronic properties are analyzed by utilizing the computer simulation, and it has been found that the obtained dark current density is is close agreement with the analytical expression. And detector is able to achieve high efficiency and detectivity by blocking the majority charge current density and surface leakage current without suppressing the photocurrent density. In this work, more than 10 to the 8 times enhancement in the photocurrent density under the cell power mode is achieved due to the efficient separation of the charge carrier. The proposed detector will demonstrate the fast response time, which is less than 1 picosecond. Detector has the optimal response in the long wavelength infrared region with the highest photocurrent responsivity, quantum efficiency, detectivity, and lowest noise signal power value of 7.82 ampere per watt, 91.44%, 4.48 into 10 to the 14 centimeter square root of hertz per watt, and 1.41 into 10 to the minus 18 watt at minus 0.5 volt. This exceptional performance is due to the combined effect of the device design, the large internal electric field across the hetero interfaces, and a high barrier height in the connection band, which effectively collects the photo-induced carrier. The proposed GPP detector has also been seen to exhibit a hot carry multiplication effect, suppressing its potential use as a temperature control variable gain IR detectors. So this is all about my this work. Thank you.